Hello there. It is good to have you with us again. Find a comfortable position, let your breathing slow, and allow the weight of the day to settle. Tonight, we are going to witness something extraordinary. We are going to watch the entire universe come into existence. 14 billion years ago, everything you have ever seen, every star, every galaxy, every atom in your body was compressed into a point smaller than a single proton. The temperature was 10 trillion degrees. And then, in a fraction of a second shorter than any clock could ever measure, space itself began to expand. We will start at that first impossible moment, when the universe was so hot that matter could not even form. We will watch as the first hydrogen atoms appear, 380,000 years later. We will see gravity slowly pull gas clouds together until the first stars ignite, ending the cosmic dark ages. We will follow the birth of galaxies, the forging of heavy elements inside dying stars, and the long, patient cooling of the cosmos toward the universe we inhabit tonight. This is not a story of distant places. This is the story of how you came to exist. If these quiet explorations help you rest, or if they bring you a moment of wonder before sleep, please consider liking and subscribing. It helps others find their way here. Now let us go back before there were stars, back before there was light, back to the very beginning, when time itself was only a few heartbeats old. In the beginning, there is no beginning, not in the way we might imagine it. There is no darkness waiting to be filled with light, no empty stage anticipating its first actor. There is no space through which something might travel, no clock against which duration might be measured. The very concepts of before and here have no meaning. What exists, if we can call it existence, is a state so foreign to human intuition that mathematics strains to describe it. This is the Planck epoch, named for the German physicist Max Planck, who first recognized the fundamental limits of measurement in our universe. It spans from whatever came before time to approximately 10 to the negative 43 seconds. A number so small that writing it out would require 42 zeros after the decimal point before reaching the digit 1. In this inconceivably brief moment, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force are thought to be unified into a single superforce. The entire observable universe, everything that will eventually become hundreds of billions of galaxies, is compressed into a region smaller than a proton, perhaps as small as 10 to the negative 35 meters across. The temperature defies comprehension. We speak of 10 to the 32 Kelvin, roughly 100 million trillion degrees. At such energies, the distinction between matter and energy dissolves completely. Particles and antiparticles flash into existence and annihilate each other in timescales shorter than the Planck time itself. The density exceeds 10 to the 97 kilograms per cubic meter, a number so extreme that a single cubic centimeter would outweigh the entire observable universe of today by factors beyond counting. Our current physics cannot penetrate this veil. General relativity, Einstein's magnificent theory of gravity and space-time, predicts its own breakdown at these scales. Quantum mechanics, which governs the behavior of the very small, conflicts irreconcilably with gravitational effects at Planck densities. Physicists suspect that a theory of quantum gravity, perhaps string theory or loop quantum gravity, is needed to describe what actually occurs. But such a theory remains incomplete, leaving the Planck epoch shrouded in mathematical uncertainty. What we can say is that something changes. At approximately 10 to the negative 43 seconds, gravity appears to separate from the other three forces. This is the first symmetry breaking, a concept central to modern physics. Imagine a pencil balanced perfectly on its tip. It possesses rotational symmetry. No direction is preferred over another. But this state is unstable. The slightest perturbation causes it to fall, and suddenly one direction becomes special. The symmetry is broken. In the early universe, the unified superforce undergoes similar transitions, though the pencil, in this case, is the quantum field that permeates all of existence. As gravity decouples, the universe enters what physicists call the grand unification epoch. The remaining three forces, electromagnetism, the strong force, and the weak force, remain merged into a single, grand, unified force. The temperature has dropped, though dropped seems almost absurd when we speak of cooling from 10 to the 32 Kelvin to merely 10 to the 29 Kelvin. This is still 100,000 trillion degrees, hot enough that the most exotic particles theorized by physics, magnetic monopoles, super-heavy X and Y bosons, and other relics of grand unification may have formed in abundance. The grand unification epoch lasts until approximately 10 to the negative 36 seconds, when another symmetry breaking occurs. The strong nuclear force separates from the electroweak force, and this transition releases an enormous amount of energy. This energy, physicists believe, triggers the most dramatic event in cosmic history: inflation. Inflation is not expansion in the ordinary sense. It is not matter flying apart through pre-existing space. Rather, it is space itself stretching, and stretching at a rate that defies everyday intuition. In a span of time lasting perhaps from 10 to the negative 36 seconds to 10 to the negative 32 seconds, the universe increases in size by a factor of at least 10 to the 26. Some models suggest even more extreme expansion, factors of 10 to the 50 or beyond. A region smaller than a proton inflates to something larger than the currently observable universe, all in less than a trillionth of a trillionth of a trillionth of a second. The mechanism driving inflation is thought to be a quantum field called the inflaton field. Like a ball rolling down a hill, the inflaton field possesses potential energy that it releases as it transitions from a higher energy state to a lower one. But unlike an ordinary ball, the inflaton field permeates all of space, and its energy density remains nearly constant even as space expands. This creates a runaway effect. The energy density drives expansion, but expansion does not dilute the energy, so expansion accelerates further. Space doubles in size, then doubles again, then again, each doubling taking roughly 10 to the negative 37 seconds. To grasp the violence of this expansion, consider that the edge of the inflating region recedes faster than light. This does not violate relativity, which forbids objects from moving through space faster than light. Space itself has no such speed limit. During inflation, points that were once in causal contact, able to exchange signals and reach thermal equilibrium, are ripped apart so quickly that they can never communicate again. This explains one of the deepest puzzles of cosmology: why the universe appears so uniform in all directions. When we observe the cosmic microwave background radiation, the afterglow of the hot, early universe, we find that its temperature is the same to within 1 part in 100,000 across the entire sky. Regions on opposite sides of the observable universe, separated by 90 billion light-years today, have nearly identical temperatures. Yet in a universe that simply expanded at a leisurely pace from the Big Bang, these regions could never have been in contact. Light, even traveling since the beginning of time, could not have crossed between them. How then did they reach the same temperature? Inflation provides the answer. Before inflation, these regions were close enough to exchange energy and equilibrate. Inflation then stretched them apart, freezing in their shared temperature like a photograph capturing a moment. The uniformity we observe is a fossil of that brief era when the entire observable universe was smaller than an atom. But inflation does more than explain uniformity. It also explains the origin of structure. Quantum mechanics tells us that empty space is never truly empty. Virtual particles flicker in and out of existence, and quantum fields experience tiny random fluctuations. During inflation, these microscopic fluctuations are stretched to cosmic scales. A quantum ripple smaller than a proton becomes a density variation spanning millions of light-years. These variations are minute, roughly 1 part in 100,000. But they are enough. They are the seeds from which all structure will grow. Where the density is slightly higher, gravity will eventually pull matter together. Where it is slightly lower, matter will flow away toward denser regions. Over billions of years, these seeds will become galaxies, galaxy clusters, and the vast cosmic web that spans the observable universe. The largest structures in existence, filaments of galaxies stretching hundreds of millions of light-years, trace their origin to quantum fluctuations during inflation, stretched and amplified by the exponential expansion of space. At approximately 10 to the negative 32 seconds, inflation ends. The inflaton field reaches the bottom of its potential energy hill and begins to oscillate. These oscillations decay into a flood of particles and radiation, reheating the universe to temperatures approaching 10 to the 27 Kelvin. This process, called reheating, populates the cosmos with the quarks, leptons, and gauge bosons that will eventually form all matter. The universe is now a seething plasma of fundamental particles, unimaginably hot and dense, but finally describable by physics we understand. The Planck epoch and inflation together last less than a billionth of a trillionth of a trillionth of a second. Yet in this vanishingly brief interval, the fundamental architecture of the cosmos is established. The forces of nature have begun their separation. Space has been stretched smooth and flat. The quantum seeds of all future structure have been planted. What follows will unfold over billions of years, but the blueprint is already drawn. The universe emerges from inflation like a pressure cooker suddenly opened, flooding with energy. At 10 to the minus 12 seconds after the Big Bang, the cosmos has cooled to approximately 10 to the 15 Kelvin, still 100 million times hotter than the core of our sun, but cool enough for a profound transformation to occur. The electroweak force, which has governed particle interactions since the end of inflation, now fractures into 2 distinct forces: electromagnetism and the weak nuclear force. This symmetry breaking, mediated by the Higgs field settling into its lowest energy state, gives mass to the W and Z bosons while leaving photons massless. The universe has just acquired one of its most fundamental properties, the mechanism by which particles gain their inertia. What exists at this moment defies everyday intuition. The cosmos is filled with a quark-gluon plasma, a state of matter so hot and dense that the strong nuclear force cannot bind quarks into the protons and neutrons we know today. Imagine a soup where the ingredients refuse to combine, where the heat is so intense that any structure attempting to form is immediately torn apart. Quarks, the fundamental building blocks that come in 6 flavors called up, down, charm, strange, top, and bottom, swim freely through this primordial medium, accompanied by their force-carrying partners, the gluons. The density is staggering. Approximately 10 to the 39th particles occupy every cubic centimeter, packed more tightly than the core of a neutron star. The gluons deserve special attention, for they behave unlike any other force carrier in nature. While photons, the carriers of electromagnetism, do not interact with each other, gluons carry the color charge of the strong force, and therefore interact with themselves. This self-interaction creates a phenomenon called color confinement. Under normal conditions, quarks can never be isolated because the energy required to separate them creates new quark-antiquark pairs. But at these extreme temperatures, exceeding 2 trillion Kelvin, the quarks are deconfined. They experience what physicists call asymptotic freedom, moving almost independently despite their close proximity. The strong force, paradoxically, becomes weaker at shorter distances and higher energies. This quark-gluon plasma is not merely theoretical speculation. In the early 21st century, particle accelerators like the relativistic heavy ion collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN recreated tiny droplets of this primordial matter by smashing gold or lead nuclei together at nearly the speed of light. These experiments revealed something unexpected. The quark-gluon plasma behaves not like a gas, as many had predicted, but like a nearly perfect liquid with the lowest viscosity of any known substance. It flows with almost no internal friction, responding to disturbances with collective waves that ripple through the medium like sound waves through air. As the universe continues its relentless expansion, the temperature drops. By 10 to the minus 6 seconds, 1 microsecond after the Big Bang, the cosmos has cooled to approximately 2 trillion Kelvin, crossing a critical threshold. The quark-gluon plasma can no longer sustain itself. Quarks begin to bind together through the strong force, forming composite particles called hadrons. This transition, known as hadronization or the QCD phase transition, represents one of the most dramatic transformations in cosmic history. The free quarks condense into protons and neutrons, each containing 3 quarks bound by gluon exchange. A proton consists of 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. The mass difference between them, the neutron is heavier by approximately 1.3 million electron volts, will later prove crucial for the chemistry of the universe. But hadronization produces more than just protons and neutrons. The cooling plasma generates a zoo of short-lived particles, pions, kaons, lambda baryons, sigma particles, and dozens of other exotic hadrons. Most of these decay within fractions of a microsecond, their constituent quarks rearranging into more stable configurations. The pions composed of a quark and an antiquark are among the longest-lived of these transient species, persisting for about 26 nanoseconds before decaying into muons and neutrinos. This cascade of creation and destruction fills the universe with a constantly shifting population of particles, each transformation governed by the conservation laws of energy, momentum, and quantum numbers. Throughout this epoch, matter and antimatter exist in nearly equal quantities. For every proton, there is an antiproton, for every electron, a positron. When particle meets antiparticle, they annihilate in a flash of pure energy, converting their combined mass into gamma-ray photons, according to Einstein's famous equation. Yet the universe we observe today is made almost entirely of matter. This asymmetry, one of the deepest mysteries in physics, must have arisen from a slight imbalance in the early universe. Approximately one extra matter particle for every billion matter-antimatter pairs. The precise mechanism remains unknown, though it likely involves subtle violations of charge parity symmetry in the weak nuclear force. Processes that treated matter and antimatter slightly differently during these first microseconds. The neutrinos produced during this epoch deserve mention, for they will carry information about these earliest moments across all of cosmic time. These ghostly particles, interacting only through the weak force and gravity, are produced copiously in the hot plasma. Unlike photons, which will remain trapped in the dense medium for hundreds of thousands of years, neutrinos decouple from matter when the universe is approximately 1 second old, streaming freely through space. A cosmic neutrino background permeates the universe to this day, cooled to just under 2 Kelvin, 2.9 Kelvin, carrying an imprint of conditions when the cosmos was mere seconds old. Detecting this relic radiation remains one of the great challenges of observational cosmology. The energy density of the universe during the quark epoch is almost incomprehensible. Each cubic centimeter contains roughly 10 to the 34th joules, enough energy, if converted, to power human civilization for billions of years. Yet this energy is distributed among countless particles moving at relativistic speeds, their kinetic energy comparable to their rest mass. The universe is radiation-dominated, meaning that the energy density of photons and relativistic particles far exceeds that of matter. This dominance shapes the expansion rate, causing the cosmos to grow proportionally to the square root of time, rather than following the slower expansion that will characterize later epochs. As the microsecond mark approaches, the universe has transformed from an undifferentiated plasma of quarks and gluons into a seething mixture of protons, neutrons, electrons, positrons, neutrinos, and photons. The building blocks of all future atoms now exist, though they remain far too energetic to combine. The temperature, still exceeding 1 trillion Kelvin, ensures that any nucleus attempting to form would be immediately shattered by the surrounding radiation. The universe must cool further, by a factor of nearly 1 million, before the next great synthesis can begin. But the raw materials are ready, forged in the first microsecond from the energy released at the end of inflation, waiting for the cosmos to cool enough for chemistry to become possible. The cooling continues, Second by second, the universe expands and its temperature drops, following the inexorable logic of thermodynamics. By 1 second after the Big Bang, the cosmos has cooled to approximately 10 billion Kelvin, still unimaginably hot by any earthly standard, yet cool enough for a critical change to occur. The neutrinos, those ghostly particles that interact so weakly with matter, now decouple from the rest of the universe. They stream away freely, no longer colliding frequently enough with other particles to maintain thermal equilibrium. This cosmic neutrino background still exists today, filling all of space at a temperature of roughly 1.95 Kelvin, though we have yet to detect it directly. The neutrinos carry away information about this moment, frozen in their distribution like a photograph taken 1 second after creation. At this same moment, a delicate balance tips. Protons and neutrons, which have been freely converting into one another through weak nuclear interactions, begin to freeze into a fixed ratio. The conversion requires energy. Neutrons are slightly heavier than protons, by about 1.3 million electron volts, roughly 0.14% of their total mass. As the temperature drops below the threshold needed to power these conversions, the ratio settles at approximately 7 protons for every neutron. This seemingly arbitrary number will determine the chemical composition of the entire universe. But neutrons face a problem. Unlike protons, free neutrons are unstable. Left alone, a neutron will decay into a proton, an electron, and an antineutrino with a half-life of about 10 minutes and 12 seconds. The clock is ticking. If the universe cools too slowly, all the neutrons will decay before they can be captured into stable nuclei, and the cosmos will contain nothing but hydrogen. The race between cosmic cooling and neutron decay will determine whether heavier elements can form at all. The minutes pass. At around 100 seconds, just over a minute and a half after the Big Bang, the temperature has dropped to approximately 1 billion Kelvin. This is roughly 70 times hotter than the core of our Sun, yet finally cool enough for nuclear fusion to proceed without the products being immediately torn apart by energetic photons. The epoch of Big Bang nucleosynthesis begins. The process starts simply. A proton and a neutron collide and stick together, forming deuterium, heavy hydrogen, with 1 proton and 1 neutron bound by the strong nuclear force. This reaction releases energy in the form of a gamma-ray photon carrying away 2.22 million electron volts. But deuterium is fragile. Its binding energy is low enough that the still intense radiation field can easily photodisintegrate it, breaking it back into its constituent particles. This creates what cosmologists call the deuterium bottleneck. Until the universe cools sufficiently for deuterium to survive, no heavier nuclei can form, because deuterium is the necessary stepping stone to everything else. The bottleneck breaks at around 3 minutes. The temperature has now fallen to roughly 900 million Kelvin, and the photons no longer carry enough energy on average to destroy deuterium nuclei. Suddenly, the deuterium that forms can persist long enough to participate in further reactions. The nuclear cooking begins in earnest. The pathways branch and multiply. Deuterium captures another proton to form helium-3, a light isotope with 2 protons and 1 neutron. Alternatively, deuterium captures a neutron to form tritium, with 1 proton and 2 neutrons. These intermediate nuclei are themselves unstable or reactive, quickly combining further. Two deuterium nuclei can fuse directly to form helium-4, releasing a proton or neutron in the process. Helium-3 can capture a neutron or fuse with another helium-3. Tritium can capture a proton. All roads lead to helium-4, the most tightly bound light nucleus, with 2 protons and 2 neutrons held together by 28.3 million electron volts of binding energy. The reactions proceed with extraordinary efficiency. Nearly every available neutron ends up bound inside a helium-4 nucleus. With the initial ratio of 7 protons to 1 neutron, and accounting for some neutron decay during the waiting period, the final result is approximately 1 helium-4 nucleus for every 12 hydrogen nuclei by number. By mass, this translates to roughly 24 to 25% helium and 75 to 76% hydrogen. This prediction, derived purely from nuclear physics and the measured expansion rate of the universe, matches observations of the oldest, most pristine gas clouds with remarkable precision, one of the great triumphs of Big Bang cosmology. But the nuclear synthesis does not stop cleanly at helium-4. Small amounts of other nuclei form as well, their abundance is determined by the specific reaction rates and the narrow window of time available. Deuterium itself survives in trace amounts, about 0.0025% by mass, because not every deuterium nucleus finds a reaction partner before the universe cools below the threshold for fusion. This leftover deuterium is cosmologically precious. It cannot be produced in significant quantities by any known stellar process. Stars destroy deuterium rather than create it. Every deuterium atom in existence today was forged in these first 20 minutes, making its measured abundance a sensitive probe of conditions in the early universe. Helium-3 also survives in small quantities, roughly 0.001% by mass. And lithium-7, with 3 protons and 4 neutrons, forms through a chain of reactions involving beryllium-7 as an intermediate. The predicted primordial lithium abundance is approximately 1 atom for every 10 billion hydrogen atoms. Curiously, observations of old stars suggest somewhat less lithium than predicted, a discrepancy known as the cosmological lithium problem that remains incompletely understood. Whether the solution lies in stellar physics, nuclear physics, or something more exotic remains an open question. Heavier elements do not form. The absence of stable nuclei with 5 or 8 nucleons creates an insurmountable gap. Helium-4 cannot easily capture another proton or neutron to build heavier elements, because helium-5 and lithium-5 are unbound, decaying in less than a trillionth of a second. Similarly, 2 helium-4 nuclei cannot fuse to form beryllium-8, which is unstable and falls apart in about 10 to the minus 16 seconds. In stellar cores, this gap is bridged by the triple alpha process, where 3 helium nuclei combine nearly simultaneously. But this requires densities and timescales unavailable in the rapidly expanding early universe. The primordial cosmos produces hydrogen, helium, and traces of lithium. Nothing more. By 20 minutes after the Big Bang, the epoch of nucleosynthesis ends. The temperature has dropped below 300 million Kelvin, too cool for nuclear fusion to continue. The density has fallen as well, as the universe has expanded by a factor of several hundred since the 1-second mark. The nuclear reactions freeze out, their products locked in place. The cosmic inventory is set. Roughly 75% hydrogen by mass, 25% helium-4, with trace amounts of deuterium, helium-3, and lithium-7. This composition will remain essentially unchanged for hundreds of millions of years until the first stars ignite and begin the slow process of stellar nucleosynthesis. The universe at 20 minutes is still a plasma, still opaque, still far too hot for neutral atoms to exist. Electrons and positrons continue to annihilate, adding their energy to the photon bath. The matter and radiation remain tightly coupled, the photons scattering endlessly off free electrons like light trapped in fog. But the fundamental building blocks of all future chemistry now exist. The protons that will eventually form the hydrogen in water, the helium that will one day fill balloons and cool superconducting magnets, the lithium that will power batteries billions of years hence. All of it was forged in this brief window, in a universe younger than a typical coffee break, at temperatures that would vaporize any known material. The precision of this process is remarkable. The abundances depend sensitively on a single parameter, the ratio of baryons to photons in the universe, a number close to 6 times 10 to the minus 10. 1 baryon, 1 proton or neutron for every 1.6 billion photons. This ratio, determined by the slight matter-antimatter asymmetry established in the first microsecond, controls the timing of the deuterium bottleneck and thus the efficiency of helium production. A higher baryon density would mean more collisions, faster reactions, and more complete conversion of deuterium into helium. A lower density would leave more deuterium unprocessed. The observed abundances constrain this ratio precisely, providing an independent measure of the total amount of ordinary matter in the universe, a value that agrees with measurements from the cosmic microwave background made billions of years later. The universe continues to expand and cool, carrying its cargo of freshly minted nuclei into the future. The plasma remains featureless, without structure, without stars, without light beyond the thermal glow of the radiation itself, but the raw materials for everything that will come. Every planet, every ocean, every living cell now exist in their most primitive form, waiting for gravity and time to sculpt them into complexity. The plasma drifts through time, expanding, cooling, carrying its precious cargo of hydrogen and helium nuclei through the featureless glow. For hundreds of thousands of years, this is all there is. A universe filled with light that cannot travel, trapped in an endless dance, with free electrons that scatter every photon before it can journey more than a few centimeters. The cosmos is opaque, a fog of charged particles and radiation so thoroughly intertwined that they move as one substance, a single fluid of matter and light. At 100,000 years after the Big Bang, the temperature has fallen to approximately 10,000 Kelvin, still hot enough to keep hydrogen fully ionized, its electrons stripped away and wandering freely through the plasma. The density has dropped enormously compared to the first minutes, yet the universe remains a prison for light. Every photon that emerges from the thermal bath immediately encounters an electron, scatters in a random direction, and loses all memory of where it was heading. Information cannot propagate. Structure cannot form. The universe waits. The physics governing this era is remarkably simple. The expansion of space stretches all wavelengths, cooling the radiation according to a precise relationship. Temperature falls inversely with the scale factor of the universe. As the cosmos doubles in size, its temperature halves. This cooling follows an elegant mathematical curve, predictable billions of years in advance or in retrospect. At 300,000 years, the temperature reaches approximately 4,000 Kelvin. The universe is now cool enough that something unprecedented becomes possible. Hydrogen nuclei, single protons that have drifted alone since the first microsecond, begin to capture electrons. This process, called recombination despite the fact that electrons and protons have never been combined before, marks one of the most significant transitions in cosmic history. The binding energy of a hydrogen atom is 13.6 electron volts, corresponding to a temperature of roughly 158,000 Kelvin. Yet recombination does not occur until the universe cools far below this threshold. The reason lies in the overwhelming number of photons compared to atoms, approximately 1 billion photons for every proton. Even when most photons lack the energy to ionize hydrogen, the rare high-energy photons in the tail of the thermal distribution are numerous enough to keep atoms ionized. Only when the temperature drops sufficiently that even these energetic photons become scarce can neutral atoms finally form and survive. At 380,000 years after the Big Bang, the temperature reaches approximately 3,000 Kelvin, roughly the temperature of a red giant star's surface, or a candle flame. The universe glows with the color of cooling iron, a deep orange-red that fills all of space. And now, finally, the electrons begin to settle into their atomic orbits. Protons capture electrons and hold them. Helium nuclei, with their stronger positive charge, capture 2 electrons each. Within a cosmologically brief window of perhaps 100,000 years, the universe transforms from a plasma of free charges into a gas of neutral atoms. The consequences are immediate and profound. Neutral hydrogen is nearly transparent to most wavelengths of light. Photons that have been trapped since the universe was a fraction of a second old suddenly find themselves free. The fog lifts. Light streams outward in all directions, carrying with it a snapshot of the universe at this precise moment, a record of the temperature, density, and composition of the cosmos when it was 380,000 years old. This light is the cosmic microwave background radiation, and it has been traveling ever since. As the universe expands, the wavelengths of these photons stretch along with space itself. Light that was emitted at 3,000 Kelvin, glowing orange-red, has been stretched by a factor of approximately 1,100 over the past 13.8 billion years. Today, that ancient glow has cooled to just 2.725 Kelvin, less than 3 degrees above absolute zero, and its peak wavelength has shifted from the visible spectrum deep into the microwave band. This is why we call it the cosmic microwave background, though it was born as visible light. The uniformity of this radiation is staggering. Measurements from satellites like COBE, WMAP, and Planck have mapped the cosmic microwave background across the entire sky with extraordinary precision. The temperature is the same in every direction to within 1 part in 100,000. This uniformity reflects the smoothness of the early universe, the legacy of cosmic inflation that stretched quantum fluctuations into near-perfect homogeneity. The universe at recombination was almost, but not quite, perfectly uniform. Those tiny deviations from uniformity, temperature variations of roughly 0.00001 Kelvin from one patch of sky to another, are the seeds of all cosmic structure. Regions that were slightly denser than average at recombination had slightly higher temperatures, while underdense regions were slightly cooler. These variations, mapped in exquisite detail by modern instruments, reveal the acoustic oscillations that rippled through the primordial plasma before recombination. The physics of these oscillations is elegant. In the plasma era, regions of higher density experienced two competing forces. Gravity pulled matter inward, trying to collapse the overdensity further. But the radiation trapped within the plasma exerted pressure, pushing outward against compression. These two forces created oscillations, sound waves propagating through the universe at roughly 60% of the speed of light. The waves could not travel faster because the plasma was heavy with matter, and the photons providing the pressure were constantly scattered, slowing their effective speed. When recombination occurred, these oscillations froze in place. The photons decoupled from matter and streamed away freely, preserving the pattern of compressions and rarefactions at that instant. The cosmic microwave background is essentially a photograph of sound waves caught mid-oscillation, frozen by the sudden transparency of the universe. The characteristic size of these oscillations is determined by how far sound could travel from the Big Bang until recombination, a distance called the sound horizon. This works out to approximately 450,000 light-years in co-moving coordinates, or about 1 degree on the sky as seen today. The cosmic microwave background shows a distinctive pattern of hot and cold spots with this characteristic angular size, a direct measurement of the geometry and composition of the universe. From these patterns, cosmologists have extracted remarkably precise values for fundamental parameters. The total density of the universe is measured to be within 0.4% of the critical density required for flat geometry. Ordinary matter, protons, neutrons, electrons, everything that makes up stars and planets and people, constitutes only 4.9% of the total energy content. Dark matter, invisible and detectable only through gravity, makes up 26.8%. The remaining 68.3% is dark energy, the mysterious component driving the accelerating expansion of the cosmos. As the photons depart and the universe becomes transparent, matter finds itself suddenly alone. For the first time, gravity can act without the counterbalancing pressure of trapped radiation. The slight overdensities imprinted by inflation and shaped by acoustic oscillations begin their slow gravitational collapse. But this collapse is extraordinarily gradual. The density contrasts are tiny, 1 part in 100,000, and the expansion of the universe works against gravitational attraction. The universe enters what astronomers call the Dark Ages. There are no stars yet, no sources of light beyond the fading glow of the cosmic microwave background. The gas is neutral hydrogen and helium, cooling as the universe expands, drifting through darkness. The temperature of the matter drops below the temperature of the radiation for the first time, as atoms can cool more efficiently than photons. By a few million years after the Big Bang, the gas temperature has fallen to just tens of Kelvin, far colder than the cosmic microwave background. In this darkness, gravity works patiently. The overdense regions attract surrounding matter, growing slowly denser. The underdense regions empty out, becoming voids. The seeds of the cosmic web are planted, though hundreds of millions of years will pass before the first structures become dense enough to collapse and ignite. The universe is pregnant with potential, carrying in its subtle density variations, the blueprints for every galaxy, every star, every planet that will ever exist. The darkness deepens. For 100 million years, the universe drifts in what astronomers call the cosmic dark ages, a period of profound quiet between the fading glow of recombination and the first stellar fires. The cosmic microwave background continues to cool, its peak wavelength stretching from visible light into the infrared, then into the microwave spectrum. By 50 million years after the Big Bang, the radiation temperature has dropped to roughly 80 Kelvin. By 100 million years, it hovers near 40 Kelvin. The universe is cold, dark, and patient. Yet within this darkness, gravity never rests. The slight density variations imprinted during inflation, amplified through 400,000 years of acoustic oscillations in the primordial plasma, now serve as the scaffolding for cosmic structure. Where the density exceeds the average by even a fraction of a percent, matter flows inward. Dark matter, which outmasses ordinary matter by roughly 5 to 1, dominates this process. It feels no electromagnetic force, emits no light, experiences no pressure. It responds only to gravity, and gravity draws it inexorably toward the overdense regions. The first structures to collapse are small by cosmic standards. Dark matter halos with masses of perhaps 100,000 to 1 million solar masses begin to condense when the universe is roughly 30 million years old. These mini-halos, as cosmologists call them, are far smaller than the Milky Way, which contains roughly 1 trillion solar masses of dark matter. They form at the nodes of the cosmic web, where filaments of dark matter intersect. The ordinary matter, still in the form of neutral hydrogen and helium gas, follows the dark matter's gravitational lead, falling into the potential wells that the dark matter creates. The gas behaves differently than the dark matter. As it falls inward, it compresses. Compression generates heat. The hydrogen and helium atoms collide more frequently, their kinetic energy increasing. In a universe with heavier elements, this heat would radiate away efficiently. Carbon, oxygen, and nitrogen atoms can be excited by collisions and then emit photons at specific wavelengths, carrying energy out of the cloud. This cooling allows the gas to compress further, accelerating the collapse. But the primordial gas contains no carbon, no oxygen, no nitrogen. The only cooling mechanism available involves molecular hydrogen, H2, formed when 2 hydrogen atoms bond together. Molecular hydrogen can rotate and vibrate, and transitions between these quantum states allow it to emit photons in the infrared. However, molecular hydrogen is a poor coolant compared to heavier molecules. Its lowest rotational transition requires a temperature of roughly 500 Kelvin to excite, and even then the emission rate is modest. The primordial gas cools slowly, reluctantly. This inefficient cooling has profound consequences. In the modern universe, gas clouds can fragment into many small clumps, each collapsing to form a star of modest mass. The Sun at one solar mass is typical. Most stars in the Milky Way are actually smaller, with red dwarfs of 0.1 to 0.5 solar masses being the most common. But in the primordial universe, the gas cannot cool efficiently enough to fragment into small pieces. Instead, the collapsing clouds remain warm, with temperatures of several hundred Kelvin, and the thermal pressure prevents fragmentation. The result is that each mini-halo produces only one or a few stars, and these stars are massive. Computer simulations of primordial star formation, run on supercomputers over thousands of processor hours, consistently predict that the first stars had masses between roughly 50 and 300 solar masses. Some models suggest even larger masses, perhaps up to 1,000 solar masses, though these extreme cases remain debated. For comparison, the most massive stars in the modern universe rarely exceed 100 solar masses, and they are exceedingly rare. The first stars, called Population 3 stars by astronomers, were giants unlike anything that exists today. The collapse proceeds through stages. First, the dark matter halo virializes, meaning its constituent particles reach a statistical equilibrium where their random motions balance the gravitational pull. The gas falls into this halo, shock heating to the virial temperature, which for a mini-halo is roughly 1,000 Kelvin. The molecular hydrogen forms through a two-step process. First, a free electron attaches to a hydrogen atom to form a negative hydrogen ion, H-. Then this ion reacts with another hydrogen atom to produce H2 and release the electron. The molecular hydrogen fraction reaches perhaps 1 part in 1,000, enough to begin cooling the gas. Over roughly 1 million years, the gas at the center of the halo cools and contracts, forming a dense core. The density rises from perhaps 1 particle per cubic centimeter to 1 million particles per cubic centimeter, then to 1 billion. At these densities, the gas becomes optically thick to its own cooling radiation, meaning the photons emitted by molecular hydrogen are reabsorbed before they can escape. The cooling stalls, and the core heats up again, reaching temperatures of roughly 2,000 Kelvin. At 2,000 Kelvin, a new process begins. The molecular hydrogen dissociates, breaking apart into individual hydrogen atoms. This dissociation absorbs energy, temporarily allowing the collapse to continue. The core contracts further, its density climbing toward 10 to the 22nd particles per cubic centimeter. At this point, the gas becomes fully opaque, trapping all radiation. The collapse becomes adiabatic, meaning no heat escapes. The temperature rises rapidly as gravitational energy converts to thermal energy. When the central temperature reaches roughly 10 million Kelvin and the density exceeds 10 to the 24th particles per cubic centimeter, nuclear fusion ignites. Hydrogen nuclei, protons, begin fusing into helium through the proton-proton chain, and at these high temperatures, the CNO cycle would dominate if carbon were present. But there is no carbon yet. The first stars burn hydrogen through the proton-proton chain, though at their extreme core temperatures, approaching 100 million Kelvin. They also produce helium through the triple alpha process almost immediately, building carbon from helium nuclei. The first star is born. The moment of ignition occurs perhaps 100 to 200 million years after the Big Bang, though the exact timing depends on the local density and the efficiency of molecular hydrogen formation. This star, blazing with a surface temperature of roughly 100,000 Kelvin, is blue-white and intensely luminous. A star of 100 solar masses produces roughly 1 million times the luminosity of the Sun. Its radiation pours into the surrounding darkness, the first starlight the universe has seen in hundreds of millions of years. The ultraviolet photons from this first star immediately begin transforming the surrounding gas. Photons with energies above 13.6 electron volts can ionize hydrogen, stripping electrons from atoms. The region around the star becomes an expanding bubble of ionized gas, a Strömgren sphere, growing outward at thousands of kilometers per second. Within this bubble, the gas is hot, roughly 10,000 Kelvin, and fully ionized. The neutral hydrogen that filled the universe since recombination begins to retreat. But the first star's life is brief. Massive stars burn through their nuclear fuel at prodigious rates. While the Sun will shine for roughly 10 billion years, a star of 100 solar masses exhausts its hydrogen in merely 2 to 3 million years. The core contracts, heats, and begins fusing helium into carbon through the triple alpha process. This stage lasts perhaps a few 100,000 years. Then carbon fuses to neon, neon to oxygen, oxygen to silicon, each stage shorter than the last. Silicon burning, the final stage, produces iron in the core and lasts only about a day. Iron is the end of the line for fusion. Fusing iron nuclei absorbs energy rather than releasing it, because iron 56 has the highest binding energy per nucleon of any element. The core, now composed of iron, can no longer generate the pressure needed to support the star against gravity. In less than a second, the core collapses. For a star of this mass, the collapse does not halt at a neutron star. The mass is too great. The core continues collapsing, forming a black hole of perhaps 40 to 60 solar masses. The outer layers of the star, still rich in lighter elements, may be ejected in a violent explosion, a pair instability supernova for stars in the range of 140 to 260 solar masses, or they may fall directly into the black hole for more massive or less massive progenitors. The pair instability mechanism occurs when the core temperature exceeds roughly 1 billion Kelvin, and gamma rays begin converting into electron-positron pairs. This pair production reduces the radiation pressure supporting the star, triggering a runaway collapse that reverses into a thermonuclear explosion, completely destroying the star and leaving no remnant. The explosion, if it occurs, disperses the first heavy elements into the surrounding gas. Carbon, oxygen, silicon, iron, all synthesized in the star's brief life, now seed the primordial medium. These elements will be incorporated into the next generation of stars, enabling more efficient cooling, smaller stellar masses, and the rich chemistry that eventually leads to planets and life. The first stars are cosmic alchemists, transforming the simple hydrogen and helium of the Big Bang into the periodic table. Across the universe, in thousands and then millions of mini-halos, this process repeats. Each halo produces its massive star or stars. Each star burns briefly and dies spectacularly. Each death enriches the cosmos with heavy elements. The Dark Ages end not with a single dawn, but with a gradual brightening, as more and more stars ignite, their ultraviolet radiation carving ionized bubbles that grow and eventually merge. This process, called cosmic reionization, transforms the universe from a neutral fog into the transparent, ionized medium we observe today. The bubbles of ionized hydrogen continue to expand, merging like soap bubbles, touching in slow motion until the entire universe becomes transparent to ultraviolet light. By roughly 1 billion years after the Big Bang, cosmic reionization is largely complete. The fog has lifted, and now, in this newly transparent cosmos, the true architecture of the universe begins to reveal itself. Gravity has been working patiently since the moment of recombination, amplifying the subtle density variations imprinted during inflation. Those tiny ripples in the primordial plasma, variations of perhaps 1 part in 100,000, have grown steadily more pronounced. Where matter was slightly denser, gravity pulled in more material. Where it was slightly less dense, matter drained away toward the overdense regions. This process, called gravitational instability, operates with mathematical precision described by equations first written by James Jeans in 1902, though the full picture requires the framework of general relativity that Einstein would provide 13 years later. The growth of structure follows a hierarchical pattern. Small objects form first, then merge to create larger ones. The mini-halos that hosted the first stars, with masses of perhaps 100,000 to 1 million solar masses, begin to fall toward one another, drawn by their mutual gravitational attraction. They collect along filaments of dark matter that stretch across millions of light years, like beads sliding along invisible threads. At the intersections of these filaments, where multiple streams of matter converge, the first true galaxies begin to assemble. Dark matter dominates this process. For every kilogram of ordinary matter in the universe, there are approximately 5 kilograms of dark matter. This mysterious substance, which interacts with ordinary matter only through gravity, collapsed first, creating the scaffolding upon which visible structures would later form. Computer simulations of cosmic structure formation, run on supercomputers processing trillions of calculations, reveal that dark matter organizes itself into a vast network of halos connected by filaments surrounding enormous empty voids. This is the cosmic web, a structure so vast that it can only be appreciated on scales of hundreds of millions of light years. The filaments of the cosmic web are not uniform tubes, but rather complex braided structures where dark matter and gas flow toward the nodes where galaxies form. Gas falling along these filaments reaches temperatures of 100,000 to 10 million Kelvin, heated by the conversion of gravitational potential energy into thermal motion. This warm, hot, intergalactic medium, as astronomers call it, contains perhaps half of all the ordinary matter in the universe today, though it remained largely invisible to telescopes until the development of X-ray observatories and ultraviolet spectrographs. Within the growing dark matter halos, ordinary matter behaves differently than its invisible counterpart. While dark matter can only clump under gravity, ordinary matter can radiate energy away as light. This cooling allows gas to sink toward the centers of halos, condensing into increasingly dense configurations. The gas settles into rotating disks, supported against further collapse by angular momentum inherited from the slight spinning motions present in the primordial material. These disks of cooling gas become the birthplaces of stars, the raw material from which galaxies are sculpted. The first galaxies are small by modern standards, perhaps 1,000th the mass of the Milky Way. They contain only a few million to a few 100 million solar masses of stars, embedded within dark matter halos 10 to 100 times more massive. Their stars form in bursts, triggered by the compression of gas as smaller halos merge together. Each merger event sends shock waves through the gas, compressing it to densities where gravitational collapse can proceed. Star formation rates in these early galaxies reach perhaps 10 to 100 solar masses per year, far exceeding the modest 2 to 3 solar masses per year that the Milky Way produces today. The heavy elements forged by the first generation of stars change everything. Carbon, oxygen, silicon, and iron provide new pathways for gas to radiate away its thermal energy. A cloud of pure hydrogen and helium can only cool efficiently down to about 8,000 Kelvin through the emission of ultraviolet photons from atomic transitions. But gas enriched with even trace amounts of heavier elements can cool to just a few tens of Kelvin through the emission of infrared radiation from molecular vibrations and fine structure transitions of carbon and oxygen ions. This enhanced cooling allows gas to fragment into much smaller clumps, producing stars with masses comparable to our Sun rather than the 100 solar mass behemoths of the first generation. By 500 million years after the Big Bang, the universe contains millions of small galaxies scattered across its volume. The Hubble Space Telescope and its successor, the James Webb Space Telescope, have captured images of these ancient systems, appearing as faint red smudges in the deepest exposures ever taken. Their light has traveled for more than 13 billion years to reach our detectors, stretched by the expansion of space from ultraviolet wavelengths to infrared. When we observe these galaxies, we see them as they were when the universe was less than 4% of its current age. The merging process accelerates. Galaxies that form near one another fall together under gravity, combining their stars, gas, and dark matter into larger systems. A typical massive galaxy today has experienced perhaps 10 to 20 significant mergers over its lifetime, each one reshaping its structure and triggering new episodes of star formation. The violence of these collisions might seem catastrophic, but the distances between individual stars are so vast that direct stellar collisions almost never occur. Instead, the mergers rearrange the orbits of existing stars while compressing gas clouds to form new ones. At the centers of merging galaxies, something remarkable happens. The supermassive black holes that formed from the deaths of the first massive stars, or perhaps from the direct collapse of pristine gas clouds, find themselves drawn together. As galaxies merge, their central black holes spiral inward, losing orbital energy through a process called dynamical friction as they scatter stars in their vicinity. Eventually, the two black holes approach closely enough that gravitational wave emission becomes significant, and they spiral together in a final cataclysmic merger. These events, lasting only seconds in their final moments, release more energy than all the stars in the observable universe combined, though entirely in the form of gravitational waves rather than light. The growing black holes do not remain passive. As gas falls toward them, it forms swirling accretion disks heated to millions of degrees. Matter spiraling into a supermassive black hole releases approximately 10% of its rest mass energy as radiation, making black hole accretion the most efficient energy source in the universe, apart from matter-antimatter annihilation. The resulting objects, called quasars or active galactic nuclei, can outshine their entire host galaxies by factors of 100 or more. At their peak, around 2 to 3 billion years after the Big Bang, quasars are among the brightest objects in the cosmos, visible across billions of light years. The energy released by quasars profoundly affects their surroundings. Radiation pressure and powerful jets of relativistic particles, launched along the magnetic field lines threading the accretion disk, can heat and expel gas from the host galaxy. This feedback process regulates the growth of both the black hole and its galaxy, establishing the tight correlation observed between black hole mass and galaxy properties that persists to the present day. A supermassive black hole typically reaches a mass of about 1/1000th of its host galaxy's stellar mass before feedback effects shut down further growth. The cosmic web continues to evolve. Filaments stretch and thin as the universe expands, while nodes grow denser as more material accumulates. The voids between filaments expand and empty, their sparse contents draining towards the surrounding walls and filaments. By 1 billion years after the Big Bang, the largest voids have grown to diameters of 50 million light-years or more. By 3 billion years, some exceed 100 million light-years across. These are not truly empty spaces, but rather regions where the density of matter falls to perhaps 20% of the cosmic average. Within the densest nodes of the cosmic web, galaxy clusters begin to form. These are the most massive gravitationally bound structures in the universe, containing hundreds to thousands of galaxies embedded within a common dark matter halo. The total mass of a large cluster reaches 10 to the 15th solar masses, roughly 1,000 times the mass of the Milky Way. Most of this mass is dark matter. The ordinary matter is divided between the galaxies themselves and a diffuse hot gas that fills the space between them, heated to temperatures of 10 to 100 million Kelvin by the gravitational energy released during the cluster's formation. The hot gas glowing in X-rays between cluster galaxies tells only part of the story. Within those galaxies, within the billions of stars burning steadily through their nuclear fuel, a more intricate process unfolds. The universe at 4 billion years old contains vast quantities of hydrogen and helium, the primordial elements forged in the first 20 minutes. But the cosmos is beginning to enrich itself with something new. Heavier elements, synthesized atom by atom in the cores of stars and scattered into space through stellar winds and explosive deaths. Consider a star like the Sun, though the Sun itself will not exist for another 5 billion years. A star of 1 solar mass burns hydrogen in its core at a temperature of approximately 15 million Kelvin. At this temperature, protons move fast enough to overcome their mutual electrical repulsion and fuse through the proton-proton chain, converting hydrogen into helium and releasing energy at a rate of about 3.8 times 10 to the 26 watts. This process continues for roughly 10 billion years, the star maintaining a delicate balance between the inward pull of gravity and the outward pressure of radiation. But more massive stars live faster and die younger. A star of 8 solar masses exhausts its core hydrogen in perhaps 50 million years. A star of 25 solar masses burns through its fuel in only 7 million years. These massive stars, scattered throughout the young galaxies of the cosmic web, become the foundries where heavy elements are forged. When a massive star exhausts the hydrogen in its core, the core contracts and heats until it reaches approximately 100 million Kelvin. At this temperature, helium nuclei begin to fuse through the triple alpha process. 3 helium-4 nuclei, each containing 2 protons and 2 neutrons, combine to form carbon-12. The process is remarkably improbable. It requires 3 particles to collide nearly simultaneously. But the physicist Fred Hoyle predicted in 1954 that carbon-12 must possess an excited energy state at precisely 7.65 million electron volts to make this reaction efficient. He was correct. Without this quantum mechanical coincidence, carbon would be vanishingly rare, and the universe would contain no organic chemistry. The helium-burning phase lasts only about 1 million years for a 25 solar mass star. When the helium is exhausted, the core contracts again, heating to approximately 600 million Kelvin. Now carbon begins to fuse, producing neon, sodium, and magnesium. This phase lasts perhaps 1,000 years. The core contracts further, reaching 1 billion Kelvin, and neon burning begins, lasting only a few years. At 1.5 billion Kelvin, oxygen fuses to produce silicon and sulfur, a process that exhausts itself in months. Finally, at 3 billion Kelvin, silicon burning commences, building iron and nickel through a rapid series of reactions that consume the silicon core in approximately 1 day. The star has become an onion, layered with shells of different elements. The outermost layers still contain hydrogen. Beneath lies a helium shell, then carbon, then neon, oxygen, silicon, and finally an iron core. Each shell burns at its characteristic temperature, the heat from inner shells igniting the fusion in outer ones. The star has become a factory, simultaneously running 6 different nuclear processes, each producing elements heavier than the last. But iron is the end of the line. Iron 56 has the highest binding energy per nucleon of any element. Fusing iron does not release energy, it absorbs it. The star has spent billions of years building a poison pill at its center, an iron core that grows heavier with each passing hour, but contributes nothing to the outward pressure supporting the star against gravity. When the iron core reaches approximately 1.4 solar masses, the Chandrasekhar limit, electron degeneracy pressure can no longer support it. The core collapses in milliseconds, falling inward at velocities approaching 1/4 the speed of light. Electrons are forced into protons, converting them to neutrons and releasing a flood of neutrinos. The core density rises to approximately 10 to the 17th kilograms per cubic meter, comparable to the density of an atomic nucleus. In less than 1 second, a volume the size of Earth compresses to a sphere roughly 20 kilometers across. The outer layers of the star, still falling inward, slam into this suddenly rigid neutron core and bounce. A shockwave races outward, heated to temperatures exceeding 10 billion Kelvin. In this inferno, a process called explosive nucleosynthesis occurs. Elements heavier than iron, which cannot be produced by fusion, are created through rapid neutron capture. Free neutrons, abundant in the explosion, bombard atomic nuclei faster than those nuclei can decay. Iron captures neutrons and becomes cobalt, then nickel, then copper, zinc, gallium, germanium, the periodic table extending upward through dozens of elements in seconds. This is the R process, the rapid neutron capture process, responsible for roughly half of all elements heavier than iron. Gold, platinum, uranium, thorium. These atoms are forged in the seconds-long fury of a core collapse supernova, then expelled into space at velocities of 10,000 kilometers per second. A single supernova can release 10 to the 44th joules of kinetic energy, more than the Sun will produce in its entire 10 billion-year lifetime. The supernova remnant expands into the interstellar medium, a hot bubble of enriched gas glowing in X-rays and radio waves. Over thousands of years, it cools and mixes with the surrounding hydrogen and helium, seeding the galaxy with heavy elements. The interstellar medium grows gradually richer, its metallicity, the astronomical term for the abundance of elements heavier than helium, increasing from nearly 0 to fractions of a percent. Not all heavy elements come from supernovae. Stars of intermediate mass, between 1 and 8 solar masses, contribute through a different mechanism. As these stars age, they expand into red giants, their outer layers cooling and puffing outward while their cores contract and heat. In the asymptotic giant branch phase, these stars develop a double shell structure, with hydrogen burning in an outer shell and helium burning in an inner shell. The helium shell ignites in periodic flashes called thermal pulses that dredge material from the interior to the surface. In these thermal pulses, the S process occurs, slow neutron capture. Neutrons are released by reactions between carbon-13 and helium-4, and these neutrons are captured by iron group nuclei over time scales of thousands of years. Unlike the R process, the S process allows unstable nuclei time to decay before capturing additional neutrons, producing a different pattern of heavy elements. Strontium, barium, lead. These elements owe their cosmic abundance primarily to the S process in aging giant stars. These giant stars shed their enriched outer layers through stellar winds, losing mass at rates of 10 to the minus 7 to 10 to the minus 5 solar masses per year. The expelled material forms planetary nebulae, shells of glowing gas illuminated by the hot stellar core left behind. The core, now exposed, becomes a white dwarf, a dense remnant supported by electron degeneracy pressure, slowly cooling over billions of years. By 8 billion years after the Big Bang, the universe has been transformed. The first generation of stars, the massive population 3 objects that burned pure hydrogen and helium, have long since exploded. Their enriched remnants have mixed into the interstellar medium, been incorporated into new molecular clouds, and collapsed to form second-generation stars. These population 2 stars contain trace amounts of heavy elements, typically 1/100th to 1/10th the solar abundance. They populate the halos and bulges of galaxies, ancient stellar populations that preserve the chemical signature of early nucleosynthesis. In the disks of spiral galaxies, where gas is denser and star formation continues, the enrichment proceeds further. Each generation of stars produces more heavy elements, dies and seeds the next generation. The metallicity of the interstellar medium rises slowly, approaching the solar value of about 1.4% by mass in elements heavier than helium. This enrichment is not uniform. The dense central regions of galaxies, where star formation is most intense, become more metal-rich than the sparse outer regions. The heavy elements change everything. Carbon and oxygen allow gas clouds to cool more efficiently, radiating away energy through molecular transitions and enabling the formation of smaller, less massive stars. Silicon and iron condense into solid grains, interstellar dust, that absorbs and re-emits starlight, shaping the thermal balance of molecular clouds. These dust grains provide surfaces where hydrogen atoms can meet and combine into molecular hydrogen, accelerating the chemistry that leads to star formation. In the densest regions of molecular clouds, where temperatures drop below 20 Kelvin and densities rise above 10 to the 10 particles per cubic meter, the dust grains become coated with ices. Water, carbon dioxide, ammonia, methane. These molecules freeze onto grain surfaces, building up mantles of volatile material. The chemistry grows complex, with ultraviolet radiation and cosmic rays driving reactions that produce organic molecules. Amino acids, the building blocks of proteins, have been detected in meteorites and interstellar clouds, suggesting that the raw materials for life are synthesized in space long before planets form. The universe at 8 billion years old is chemically mature. The periodic table, empty at the moment of the Big Bang except for hydrogen and traces of helium and lithium, now extends to uranium and beyond. Every atom heavier than helium in existence has been forged in a star, in the steady fusion of main sequence burning, in the layered shells of red giants, in the cataclysmic seconds of supernova explosions. The cosmos has become a recycling system, matter flowing from interstellar clouds into stars, being processed through nuclear fire and returning enriched to the void. And so the cycle continues, the great wheel of stellar birth and death turning through the spiral arms of galaxies across the universe. In one particular galaxy, a barred spiral roughly 100,000 light-years across, unremarkable among the hundreds of billions of its kind, this recycling process is about to produce something extraordinary. The galaxy will eventually be called the Milky Way, and in one of its minor spiral arms, a cloud of gas and dust is beginning to stir. The time is approximately 9.2 billion years after the Big Bang, or roughly 4.6 billion years before the present day. The universe has aged considerably since the epoch of heavy element synthesis. Dark energy, the mysterious component that makes up roughly 68% of the cosmos, has begun to dominate over matter. The expansion of space is no longer decelerating under gravity's pull, but accelerating, pushing galaxy clusters apart at ever-increasing rates. Yet within galaxies themselves, the dance of stellar evolution continues unaffected by this cosmic acceleration. The region in question lies in what will come to be known as the Orion Spur, a minor arm branching off from the larger Sagittarius arm. Here, roughly 26,000 light-years from the galactic center, where the supermassive black hole Sagittarius A star lurks with its 4 million solar masses, a molecular cloud drifts through the interstellar medium. This cloud is not primordial hydrogen from the Big Bang, but rather a mixture enriched by generations of stellar death. It contains the ashes of perhaps dozens of supernovae, the expelled atmospheres of hundreds of red giants, the processed material of stars that lived and died over the preceding 4 billion years. The composition of this cloud tells the story of its ancestry. Hydrogen still dominates, making up roughly 70% of its mass, with helium contributing about 28%. These proportions little changed from the primordial ratios established in Big Bang nucleosynthesis. But the remaining 2%, though seemingly insignificant, makes all the difference. This fraction contains oxygen, carbon, nitrogen, silicon, magnesium, iron, and traces of every other naturally occurring element. The oxygen atoms drifting through this cloud were forged in the helium-burning shells of massive stars. The carbon came from the triple alpha process in red giant cores. The iron was synthesized in the final seconds of supernova explosions, when silicon nuclei fused in the desperate heat of stellar collapse. The cloud spans perhaps 65 light-years across, containing enough material to form several thousand stars. Its temperature hovers around 10 Kelvin, just 10 degrees above absolute zero, cold enough that hydrogen molecules move at only a few hundred meters per second. At this temperature, the cloud's own gravity can overcome the thermal pressure that would otherwise cause it to expand. The cloud is in a delicate balance, neither collapsing nor dispersing, drifting through the galaxy like a vast, cold fog. Then something disturbs this equilibrium. The exact trigger remains debated. Perhaps the shockwave from a nearby supernova, perhaps the gravitational perturbation of a passing star, perhaps the compression as the cloud entered a spiral arms density wave. Whatever the cause, a region within the cloud begins to contract. The collapse starts slowly, imperceptibly, but the mathematics of gravity are relentless. As the gas falls inward, it compresses and heats. As it heats, it radiates energy away into space. As it loses energy, it can compress further. The process feeds itself, a runaway contraction that will transform a diffuse cloud into a star. The collapsing region contains roughly 2 solar masses of material, enough to form a modest star with some material left over. As it contracts, it begins to rotate faster, like a figure skater pulling in their arms. This is the conservation of angular momentum at work, the same principle that governs spinning galaxies and orbiting planets. The rotation flattens the collapsing cloud into a disk, material falling inward along the poles while spreading outward along the equator. At the center of this disk, temperatures climb. Within perhaps 100,000 years of the initial collapse, the central concentration reaches several thousand Kelvin. It glows with infrared light, a protostar not yet hot enough to ignite nuclear fusion, but already luminous from the gravitational energy released by its contraction. This object, roughly the size of the present-day solar system, will continue to shrink and heat for another 50 million years. The disk surrounding this protostar is where the real complexity emerges. Spanning perhaps 200 astronomical units, 200 times the distance from Earth to the Sun, this protoplanetary disk contains only about 1% of the system's total mass, yet it holds all the raw material for planets, moons, asteroids, and comets. The disk is not uniform. Temperature decreases with distance from the central protostar, from over 1500 Kelvin in the inner regions to below 50 Kelvin at the outer edges. This temperature gradient creates distinct chemical zones, each with its own characteristic composition. Within roughly 4 astronomical units of the protostar, temperatures exceed the condensation point of most volatile compounds. Water cannot exist as ice here, nor can methane, ammonia, or carbon dioxide. Only refractory materials, silicates, iron, aluminum oxides, can condense into solid grains. These microscopic particles, each perhaps a micrometer across, drift through the hot inner disk, colliding and sticking together through electrostatic forces. This is the beginning of planet formation, a process called accretion that will build worlds from dust. Beyond roughly 4 astronomical units lies the frost line, also called the snow line, where temperatures drop below 170 Kelvin and water ice can exist as a stable solid. This boundary is crucial. Ice is far more abundant than rock-forming elements in the cosmic inventory, so beyond the frost line, the amount of solid material available for planet building increases dramatically, by a factor of 4 or more. The outer disk is rich with ice grains, frozen water mixed with ammonia, methane, and carbon dioxide, all condensed from the gas that pervades the disk. The process of accretion proceeds through distinct stages. First, micrometer-sized dust grains collide and stick, forming fluffy aggregates millimeters across. These aggregates continue to grow, reaching centimeter and then meter scales. At this point, the physics becomes challenging. Meter-sized boulders tend to fragment when they collide rather than stick, and they also experience significant drag from the surrounding gas, causing them to spiral inward toward the protostar. This is the meter-size barrier, a bottleneck in planet formation that theorists have struggled to explain. The solution appears to involve turbulence and local concentrations. Eddies in the disk can trap particles, creating regions of enhanced density where collisions are more frequent and growth can proceed rapidly. Some models suggest that streaming instabilities, interactions between the gas and solid particles, can concentrate materials so efficiently that kilometer-sized planetesimals form almost instantaneously through gravitational collapse, bypassing the problematic intermediate sizes entirely. However it happens, the disk soon contains countless planetesimals, rocky bodies in the inner system and icy bodies in the outer system, each a few kilometers across. These objects are large enough that their mutual gravity becomes significant. They begin to attract each other, their orbits crossing and intersecting. Collisions become more violent as the bodies grow, no longer gentle sticking, but catastrophic impacts that can shatter or merge depending on the collision speed and angle. In the inner disk, within the frost line, planetesimals accumulate into rocky protoplanets. The largest of these, through a combination of gravitational focusing and fortunate positioning, grow faster than their neighbors. They sweep up material from their orbital zones, their gravity reaching out to capture passing planetesimals. This is runaway growth, a rich-get-richer process that quickly produces a handful of dominant bodies while leaving countless smaller objects as debris. 4 rocky protoplanets emerge from this competition, orbiting at distances of roughly 0.4, 0.7, 1.0, and 1.5 astronomical units from the central star. The innermost is small, its growth stunted by the limited material available so close to the star and by the gravitational influence of its larger neighbor. The second and third are similar in size, each accumulating roughly 1 Earth mass of rocky material. The fourth is smaller still, its growth interrupted by the gravitational perturbations from the massive planet forming just beyond. Beyond the frost line, the story unfolds differently. Here, the abundance of ice means that protoplanetary cores can grow much larger before they exhaust their local supply of solid material. The largest of these cores, forming at roughly 5 astronomical units from the star, reaches a critical threshold, approximately 10 Earth masses, at which point something remarkable happens. Its gravity becomes strong enough to capture and retain hydrogen and helium gas directly from the surrounding disk. This is the birth of a gas giant. Once gas capture begins, it proceeds rapidly, the growing planet's gravity pulling in ever more material in a runaway process. Within perhaps 100,000 years, this object accumulates 300 times the mass of Earth, becoming a swirling sphere of hydrogen and helium with a dense core of rock and ice at its center. The heat of accretion makes it glow with infrared light, briefly outshining the still-forming star at certain wavelengths. A second gas giant forms at roughly 10 astronomical units, following the same process but starting later and with less material available. It reaches only 95 Earth masses, still enormous but noticeably smaller than its inner neighbor. Beyond these two giants, the disk is too sparse and the orbital timescales too long for additional gas giants to form before the disk dissipates. Instead, 2 ice giants emerge at roughly 20 and 30 astronomical units, objects of 17 and 15 Earth masses respectively, composed primarily of water, ammonia, and methane ices, with relatively thin hydrogen atmospheres. The central protostar, meanwhile, continues its contraction. Roughly 50 million years after the initial cloud collapse, its core temperature reaches 10 million Kelvin. At this threshold, hydrogen nuclei finally possess enough kinetic energy to overcome their mutual electrical repulsion and fuse into helium. Nuclear fusion ignites, and the protostar becomes a true star, a main-sequence yellow dwarf of spectral type G2 with a surface temperature of 5,800 Kelvin and a luminosity that will remain stable for the next 10 billion years. The ignition of fusion marks a turning point. The young star's radiation and stellar wind begin to clear the remaining gas from the protoplanetary disk. Within perhaps 10 million years, the disk is gone, its gas either accreted onto planets, blown away by stellar radiation, or fallen into the star itself. What remains is a planetary system. 4 rocky inner planets, 4 outer giants, and countless smaller bodies. Asteroids concentrated between the orbits of the 4th rocky planet and the first gas giant. Icy comets scattered through the outer reaches. The system is not yet stable. The giant planet's gravity stirs the remaining debris, sending asteroids and comets careening through the inner system. For several hundred million years, the rocky planets endure a bombardment of impacts, their surfaces cratered and recratered by infalling material. This late, heavy bombardment delivers water and organic molecules to the inner planets, volatile materials that originated beyond the frost line, and now find themselves deposited on warm, rocky worlds. The third planet from the star occupies a particularly favorable position. Its distance, 1 astronomical unit, or roughly 150 million kilometers, places it within the habitable zone, where temperatures allow liquid water to exist on the surface. Its mass, roughly 6 times 10 to the 24th kilograms, provides enough gravity to retain a substantial atmosphere, but not so much as to capture hydrogen and become a gas dwarf. The water delivered by comets and asteroids accumulates on its surface, forming oceans that cover much of the globe. This planet, this unremarkable rocky world orbiting an unremarkable yellow star in an unremarkable spiral arm of an unremarkable galaxy, carries within its rocks the entire history of cosmic evolution. Its iron core was forged in supernova explosions billions of years before the solar system formed. Its silicon mantle contains oxygen atoms synthesized in the helium-burning shells of red giants. Its water molecules incorporate hydrogen atoms that have existed unchanged since the first seconds after the Big Bang, combined with oxygen atoms manufactured in stellar cores. Every element heavier than hydrogen, every atom of carbon and nitrogen and phosphorus passed through at least 1 stellar generation before finding its way into this small blue world. The atoms that compose this small world connect it to a universe far vaster than any single planet, any single star, any single galaxy can suggest. To understand the present cosmos, the universe as it exists 13.8 billion years after its beginning, requires stepping back from this blue marble, back from its yellow sun, back from the spiral arms of its home galaxy, until the true architecture of existence reveals itself. The Milky Way, seen from within, appears as a band of light stretching across the night sky, but from a distance of several million light-years, its structure becomes clear. A barred spiral galaxy approximately 100,000 light-years in diameter, containing somewhere between 100 billion and 400 billion stars, rotating once every 230 million years at the position of the Sun. The central bar, a dense concentration of older, redder stars, stretches roughly 27,000 light-years across the galactic core. Spiral arms wind outward from the bar's ends, traced by young blue stars, glowing nebulae, and the dark lanes of dust that mark regions of ongoing star formation. At the very center, hidden behind 26,000 light-years of stars and dust, lies Sagittarius, a star, a supermassive black hole containing approximately 4 million solar masses compressed into a region smaller than Mercury's orbit around the Sun. Stars orbit this invisible mass at tremendous speeds. The star S2 completes its elliptical orbit in just 16 years, reaching velocities of nearly 8,000 kilometers per second at closest approach. The black hole itself emits no light, but the radio waves and X-rays from superheated gas spiraling toward its event horizon betray its presence. Yet the Milky Way is not alone. Approximately 2.5 million light-years away, the Andromeda Galaxy approaches at 110 kilometers per second, its trillion stars destined to merge with our own galaxy in roughly 4.5 billion years. Between these two giants, dozens of smaller galaxies orbit. The large and small Magellanic Clouds, visible from Earth's southern hemisphere, contain perhaps 30 billion and 3 billion stars, respectively. The Sagittarius dwarf elliptical galaxy, discovered only in 1994, is currently being torn apart by the Milky Way's tidal forces, its stars streaming into our galaxy in long arcs. Together, these galaxies and approximately 80 others form the local group, a gravitationally bound structure spanning roughly 10 million light-years. The local group itself is merely a minor component of a larger structure, the Virgo supercluster, centered on the Virgo cluster some 54 million light-years distant. The Virgo cluster alone contains over 1,000 galaxies, dominated by the giant elliptical galaxy M87, whose central black hole contains 6.5 billion solar masses and launches a jet of relativistic plasma extending 5,000 light-years into intergalactic space. But even superclusters are not the largest structures. In 2014, astronomers identified Laniakea, a supercluster complex containing the Virgo supercluster, along with the Hydra Centaurus supercluster and several others, a structure 520 million light-years across, containing approximately 100,000 galaxies with a total mass of 100 billion solar masses. Galaxies within Laniakea flow toward a gravitational focal point called the Great Attractor, a region of concentrated mass hidden behind the Milky Way's disk. The distribution of these structures across the observable universe follows a pattern that emerged from the density fluctuations imprinted during inflation. Galaxies cluster along filaments, long thread-like concentrations of dark matter and ordinary matter that stretch for hundreds of millions of light-years. Where filaments intersect, galaxy clusters form, the densest knots in the cosmic web. Between the filaments lie voids, vast regions of nearly empty space where few galaxies exist. The Botas Void, discovered in 1981, spans approximately 330 million light-years and contains only 60 galaxies where thousands might be expected. The KBC Void, identified in 2013, may extend nearly 2 billion light-years, making it one of the largest known structures, or rather, anti-structures, in the observable universe. These voids are not truly empty. They contain diffuse gas and dark matter, but at densities far below the cosmic average. The cosmic web's structure can be measured through galaxy surveys. The Sloan Digital Sky Survey has mapped the positions of over 2 million galaxies, revealing the foam-like texture of the universe at scales of hundreds of millions of light-years. At even larger scales, above roughly 1 billion light-years, the universe becomes statistically homogeneous, equally lumpy in all directions, with no preferred location or structure. This homogeneity extends to the cosmic microwave background, the ancient light released when the universe was just 380,000 years old, now cooled to 2.725 Kelvin and filling all of space. Temperature variations in this radiation amount to only 1 part in 100,000, reflecting the tiny density fluctuations that seeded all subsequent structure. The universe, at its largest scales, remains remarkably smooth, a legacy of inflation's exponential expansion. The expansion continues today, carrying galaxy clusters apart at velocities proportional to their distances. The Hubble constant, measured at approximately 70 kilometers per second per megaparsec, means that a galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. Beyond roughly 14 billion light-years, the recession velocity exceeds the speed of light, placing those regions forever beyond our observational horizon. And driving this expansion, composing 68% of the universe's total energy density, dark energy pushes space itself to expand at an accelerating rate, a cosmic pressure that will shape all future evolution. Yet even as dark energy stretches the fabric of space-time, within galaxies the ancient drama of gravity continues unabated. Stars burn through their nuclear fuel on timescales ranging from millions to trillions of years. And when that fuel exhausts, gravity, patient, inexorable, claims its due. The manner of a star's death depends almost entirely on its mass, a simple number that determines whether the stellar corpse becomes a slowly cooling ember, a city-sized ball of neutrons, or a rupture in space-time itself. Consider first the fate awaiting most stars in the universe, including our own Sun. A star of roughly 1 solar mass spends approximately 10 billion years fusing hydrogen into helium in its core, maintaining the delicate balance between gravitational compression and radiation pressure. When the core hydrogen depletes, the star swells into a red giant, its outer layers expanding to perhaps 1 astronomical unit, while the helium core contracts and heats. At temperatures exceeding 100 million Kelvin, helium nuclei begin fusing into carbon through the triple alpha process, 3 helium-4 nuclei combining to form carbon-12. Some carbon captures additional helium to become oxygen-16, but for a solar mass star, this is where nucleosynthesis ends. The core never reaches the 600 million Kelvin required to fuse carbon. Instead, the outer layers drift away as a planetary nebula, a shell of glowing gas expanding at 20 to 30 kilometers per second, while the exposed core remains behind as a white dwarf. This stellar remnant contains roughly half the original star's mass, compressed into a sphere approximately the size of Earth, yielding densities of around 1 million grams per cubic centimeter. A teaspoon of white dwarf material would weigh several tons on Earth's surface. What prevents further collapse? Not nuclear fusion. That has ceased entirely. Instead, electron degeneracy pressure supports the white dwarf against gravity. This quantum mechanical effect arises from the Pauli exclusion principle. No 2 electrons can occupy the same quantum state. As matter compresses, electrons are forced into higher and higher energy states, creating an outward pressure independent of temperature. The white dwarf will never collapse further, regardless of how much it cools. And cool it does, radiating away its thermal energy over billions of years. A newly formed white dwarf glows at surface temperatures exceeding 100,000 Kelvin, appearing blue-white. Over 10 billion years, it fades through yellow, orange, and red, eventually becoming a black dwarf, a cold, dark sphere of degenerate carbon and oxygen. The universe is not yet old enough for any black dwarfs to exist. The coolest known white dwarfs still glow faintly at temperatures around 3,000 Kelvin, having cooled for roughly 11 billion years. The Indian-American physicist Subramanian Chandrasekhar calculated in 1930 that electron degeneracy pressure has limits. If a white dwarf exceeds approximately 1.4 solar masses, now called the Chandrasekhar limit, the electrons become relativistic, moving at speeds approaching light, and degeneracy pressure can no longer support the star. This limit explains why white dwarfs in binary systems sometimes explode as type Ia supernovae. If a white dwarf accretes matter from a companion star and approaches 1.4 solar masses, carbon fusion ignites explosively throughout the core, releasing roughly 10 to the 44th joules of energy and destroying the star entirely. Stars more massive than about 8 solar masses follow a different path. Their cores grow hot enough to fuse carbon, then neon, then oxygen, then silicon, each stage proceeding faster than the last as the star desperately seeks new fuel sources. Carbon burning lasts perhaps 1,000 years, neon burning a few years, oxygen burning months, silicon burning, the final stage, lasts merely a day, producing iron 56 in the core. Iron represents the end of the fusion road. With the most tightly bound nucleus of any element, iron releases no energy when fused. Indeed, fusing iron absorbs energy. The core, now composed of iron nuclei at temperatures exceeding 5 billion Kelvin, suddenly loses its energy source. Within less than a second, a fraction of a heartbeat in cosmic terms, the core collapses. The collapse proceeds at roughly a quarter to the speed of light. In milliseconds, the iron core compresses from a sphere the size of Earth to a ball perhaps 20 kilometers across. Electrons are forced into protons, converting them to neutrons through inverse beta decay and releasing a flood of neutrinos. The density exceeds 100 trillion grams per cubic centimeter, comparable to an atomic nucleus. At this point, neutron degeneracy pressure halts the collapse, and the infalling outer layers bounce off the suddenly rigid core. This bounce, amplified by neutrino heating and hydrodynamic instabilities, drives a shockwave outward through the star. The result is a core collapse supernova, releasing roughly 10 to the 46 joules of energy, mostly in neutrinos, with only about 1% emerging as visible light and kinetic energy. For a few weeks, the supernova outshines its entire host galaxy, radiating as much visible light as 10 billion suns. The remnant left behind is a neutron star, a sphere of neutron-degenerate matter roughly 20 kilometers in diameter, containing 1.4 to 2 solar masses. The density reaches 400 trillion grams per cubic centimeter at the core. Surface gravity is roughly 200 billion times Earth's gravity. Escape velocity approaches half the speed of light. The magnetic field, compressed along with the collapsing core, intensifies to between 10 to the 8th and 10 to the 15th Tesla, trillions of times stronger than Earth's field. Neutron stars often rotate rapidly, spinning up as they collapse like a figure skater pulling in their arms. The Crab pulsar, born in the supernova observed in 1054 CE, rotates 30 times per second. Some millisecond pulsars spin at 700 rotations per second, their surfaces moving at a significant fraction of light speed. These rotating magnetic fields sweep beams of radio waves across space. When the beam crosses Earth's line of sight, we detect regular pulses with periods stable to parts per billion, nature's most precise clocks. But neutron degeneracy pressure, like electron degeneracy pressure, has limits. The Tolman-Oppenheimer-Volkoff limit, calculated in 1939, sets the maximum neutron star mass at roughly 2 to 3 solar masses, depending on the still uncertain equation of state for ultra-dense matter. Beyond this limit, no known force can halt gravitational collapse. When a stellar core exceeds this threshold, either through the collapse of a very massive star or through neutron-star mergers, gravity wins absolutely. The matter compresses past neutron star densities, past any conceivable form of degenerate matter, until it occupies zero volume and infinite density, a singularity. Surrounding this singularity, at a radius where escape velocity equals light speed, lies the event horizon, the boundary of a black hole. For a black hole of 10 solar masses, the event horizon, the Schwarzschild radius, measures roughly 30 kilometers. Nothing that crosses this boundary can return. Even light curves inward, trapped by the warped geometry of space-time. From outside, the black hole appears perfectly black, detectable only through its gravitational influence on nearby matter. When gas falls toward a black hole, it rarely plunges directly inward. Conservation of angular momentum forces the material into an accretion disk, spiraling gradually closer, while friction heats the gas to millions of Kelvin. The inner regions of the disk glow brilliantly in X-rays, converting gravitational potential energy into radiation, with efficiencies approaching 40%, far exceeding the mere 0.7% efficiency of hydrogen fusion. Black holes, paradoxically, power some of the brightest objects in the universe. These stellar remnants, white dwarfs, neutron stars, and black holes, represent the universe's method of locking away matter in increasingly compact forms, the white dwarfs cooling slowly through the galaxy's disk, the neutron stars spinning down over millions of years as their magnetic fields drain rotational energy, the black holes growing incrementally as they capture passing material. Each represents an endpoint, a stellar corpse that will persist for timescales dwarfing the current age of the universe, waiting through the long eras yet to come. The waiting has already begun. While the universe at 13.8 billion years still blazes with the light of hundreds of billions of galaxies, the seeds of a far quieter era have long been planted. The most massive stars, the blue supergiants burning through their fuel in mere millions of years, have already exhausted their brief, brilliant lives. The sun-like stars, with their 10 billion-year lifespans, are halfway through their steady hydrogen burning. But the smallest stars, the red dwarfs that constitute roughly 75% of all stars in the Milky Way, have barely begun their extraordinarily patient existence. A red dwarf of 0.1 solar masses, a star like Proxima Centauri, the nearest stellar neighbor to the Sun at 4.24 light-years distant, burns its hydrogen fuel so slowly, so efficiently, that it will continue shining for roughly 10 trillion years. This is not a typographical error. 10 trillion years. The current age of the universe represents less than 1% of such a star's total lifespan. These dim, cool objects, with surface temperatures between 2,500 and 4,000 Kelvin, compared to the Sun's 5,778 Kelvin, are fully convective. Unlike the Sun, which burns hydrogen only in its core, while the outer layers remain relatively unmixed, a red dwarf circulates its entire mass through the fusion zone. Every hydrogen atom eventually makes its way to the center, participates in nuclear burning, and contributes to the star's energy output. Nothing is wasted. Nothing is left behind. The luminosity of such stars is correspondingly modest. Proxima Centauri emits roughly 0.0017 times the Sun's luminosity, so faint that despite being the closest star to Earth, it requires a telescope to see. Yet this very faintness is the key to longevity. The rate of nuclear fusion scales steeply with stellar mass, approximately as mass to the fourth power. A star twice as massive as the Sun burns through its fuel not twice as fast, but roughly 16 times as fast. The red dwarfs, with their miserly energy budgets, will still be shining when the universe is 1,000 times its current age. As the trillions of years unfold, the stellar population of galaxies undergoes a profound transformation. The massive stars vanish first, their supernovae fading into memory, their remnants, neutron stars and black holes, drifting silently through the galactic disk. The intermediate mass stars follow, swelling into red giants, shedding their outer layers as planetary nebulae, leaving behind white dwarfs that begin their billion-year cooling trajectories. The sun-like stars, one by one, exhaust their core hydrogen, expand, and die. The galaxy grows dimmer with each passing eon. By 100 billion years from now, roughly 7 times the current age of the universe, the Milky Way's stellar population has shifted dramatically. New star formation has largely ceased. The raw material for stars, cold molecular hydrogen in giant clouds, has been consumed, expelled from the galaxy by stellar winds and supernovae, or heated to temperatures too high for gravitational collapse. The last generation of stars formed perhaps 50 billion years earlier, and even these are now aging. The galaxy's light comes increasingly from red dwarfs, their combined glow casting a dim, ruddy illumination across the spiral arms. But the galaxy itself has changed. The Andromeda Galaxy, currently approaching the Milky Way at approximately 110 kilometers per second, will have long since arrived. The collision, or more accurately, the merger, begins in roughly 4.5 billion years from the present day. The term collision is somewhat misleading. Galaxies are mostly empty space. The average distance between stars in the Milky Way's disk is roughly 4 light-years, and during the merger, direct stellar collisions will be extraordinarily rare. Perhaps a handful among hundreds of billions of stars. The merger is not a crash, but a gravitational dance, a slow interpenetration of 2 vast stellar systems. The process unfolds over approximately 1 to 2 billion years. As the galaxies approach, tidal forces begin to distort their shapes. Long streamers of stars are pulled from the outer regions, forming tidal tails that can extend hundreds of thousands of light years into intergalactic space. The spiral structure of both galaxies is disrupted, then destroyed. Stars that once followed orderly circular orbits around their galactic centers are flung onto chaotic trajectories. Some ejected entirely from the merging system, others plunging toward the center. The central supermassive black holes, Sagittarius A star at roughly 4 million solar masses, and Andromeda's black hole at approximately 100 million solar masses, spiral toward each other over hundreds of millions of years. Dynamical friction, the gravitational drag caused by interactions with surrounding stars, gradually drains their orbital energy. They circle closer, their orbital period shrinking from millions of years to thousands, then to mere years. In the final stages, they emit gravitational waves so powerful that the energy radiated exceeds the combined luminosity of all stars in the merging galaxy. The waves carry away the last of their orbital angular momentum, and the black holes merge in a final burst of gravitational radiation, forming a single black hole of roughly 100 million solar masses. The merged galaxy, sometimes called Milkomeda or Milkdromeda in speculative astronomical literature, settles into a new configuration. Without the angular momentum that maintained the original spiral structures, the combined system relaxes into an elliptical galaxy. The stars orbit the central black hole on randomly oriented paths, forming a smooth, roughly spherical distribution. The characteristic spiral arms, the sites of active star formation, are gone. The galaxy has become a stellar graveyard, its stars aging in place, no new generations arising to replace them. By 1 trillion years from now, the transformation is nearly complete. The last sun-like stars have died. The last white dwarfs have cooled to temperatures below 4,000 Kelvin, their surfaces dimming from white to yellow to orange to deep red. Only the red dwarfs remain active, their nuclear fires still burning, their convective interiors still circulating hydrogen to their cores. The galaxy glows with their collective light, a dim red luminescence, perhaps 1/10,000th of the Milky Way's current brightness. The night sky from any hypothetical planet orbiting one of these ancient red dwarfs would be transformed beyond recognition. The other galaxies of the local group have long since merged with Milkomeda or been ejected by gravitational interactions. The more distant galaxies, carried away by the accelerating expansion of space, have crossed the cosmic horizon. Light from these receding galaxies, red-shifted to longer and longer wavelengths, eventually stretches beyond detectability. The observable universe shrinks, not because the universe itself is contracting, but because the expansion carries distant objects beyond the reach of light. The night sky grows darker, emptier, the cosmic web of galaxies fading from view, until only the local merged system remains visible. Within this isolated stellar system, the red dwarfs continue their patient burning. A star of 0.08 solar masses, barely above the minimum mass required for sustained hydrogen fusion, will shine for roughly 12 trillion years. These are the last true stars, the final generation of objects powered by nuclear fusion. Their surfaces, at temperatures around 2,300 Kelvin, glow a deep crimson, barely visible to eyes adapted to sunlight. Their habitable zones, where liquid water might exist on a planetary surface, lie so close to the star that any orbiting world would be tidally locked, one face eternally lit, one face eternally dark. As even these minimal stars exhaust their hydrogen, they too will fade. Unlike more massive stars, red dwarfs do not become red giants. Their fully convective nature means they burn all their hydrogen uniformly, leaving behind a helium core that never reaches the temperatures required for helium fusion. Approximately 100 million Kelvin. Instead, they simply contract and cool, becoming helium-white dwarfs, joining the vast population of stellar remnants already drifting through the galaxy. By 100 trillion years from now, 10,000 times the current age of the universe, the last red dwarf will have exhausted its fuel. The era of starlight, which began with the first population 3 stars, roughly 100 million years after the Big Bang, will have ended. The universe will contain no objects powered by nuclear fusion. Only the remnants will remain. White dwarfs cooling toward absolute zero, neutron stars spinning down to stillness, black holes waiting in the darkness. The cosmos will have entered a new epoch, one defined not by the light of burning stars, but by the slow decay of matter itself, the gradual dissolution of structure across timescales that make even 1 trillion years seem brief. And so the universe drifts into its longest chapter, one measured not in billions or trillions of years, but in timescales so vast they require exponential notation to express. The degenerate era begins, an epoch dominated by the cold remnants of stellar evolution, by objects no longer powered by fusion, but merely persisting through the slow leak of residual heat into an ever-expanding void. The white dwarfs that once blazed at temperatures of 10,000 Kelvin or more now cool through the millennia, their crystallized carbon and oxygen cores radiating away the thermal energy accumulated during billions of years of stellar life. A white dwarf cools roughly as the inverse of time. After 10 billion years, its surface temperature might drop to 4,000 Kelvin. After 100 billion years, to perhaps 2,000 Kelvin. After 1 trillion years, to temperatures barely distinguishable from the cosmic microwave background itself. By 10 to the 15th years, 1 quadrillion years, or roughly 70,000 times the current age of the universe, even the hottest white dwarfs will have faded to temperatures below 100 Kelvin. They will emit primarily in the far infrared, invisible to any detector sensitive to optical light. The universe will have grown profoundly dark. But darkness is not emptiness, and stillness is not stability. On these immense timescales, processes too slow to matter in the stellar era become the dominant drivers of cosmic evolution. Consider the fate of galaxies themselves. Though star formation has long since ceased, the gravitational interactions between stellar remnants continue. When two objects pass close to one another, they exchange energy and momentum through gravitational scattering. Over time, these encounters redistribute energy within the galactic system. Some objects gain velocity and escape the galaxy entirely, carrying energy away with them. Others lose velocity and sink toward the galactic center. This process, called dynamical relaxation, operates on a time scale proportional to the number of objects in the system divided by the logarithm of that number multiplied by the crossing time. For a galaxy containing 100 billion stellar remnants, the relaxation timescale stretches to roughly 10 to the 19th years, 10 quintillion years. By this point, galaxies as coherent structures begin to dissolve. The outer regions evaporate as high-velocity remnants escape into intergalactic space. The inner regions contract, funneling mass toward the central supermassive black hole. Roughly 90% of a galaxy's stellar remnants will eventually be ejected into the void, scattered across distances so vast that they will never interact with another object again. The remaining 10% will spiral inward, their orbits decaying through gravitational radiation and dynamical friction until they merge with the central black hole. The supermassive black holes that once anchored galaxies will grow slightly more massive, swallowing the last remnants of their stellar populations. The intergalactic void, meanwhile, continues its relentless expansion. Dark energy, which began to dominate the universe's energy budget roughly 5 billion years ago, drives space-time apart at an accelerating rate. The Hubble parameter, currently about 70 kilometers per second per megaparsec, asymptotically approaches a constant value as the universe becomes increasingly dominated by the cosmological constant. Objects beyond a certain distance, the cosmic event horizon, recede faster than light and become forever unreachable. This horizon shrinks in co-moving coordinates as the universe ages, isolating each gravitationally bound structure in its own pocket of accessible space-time. The local group, long since merged into a single elliptical galaxy, will find itself alone in an observable universe that contains nothing else. The cosmic microwave background, already redshifted to a temperature of 2.7 Kelvin, will continue to cool as the universe expands, dropping below 1 Kelvin, then below a millikelvin, then below a nanokelvin, asymptotically approaching but never quite reaching absolute zero. On still longer timescales, the stability of matter itself comes into question. The protons and neutrons that compose ordinary matter, the baryons forged in the first microseconds after the Big Bang, may not be eternal. Grand unified theories, which attempt to merge the strong, weak, and electromagnetic forces into a single framework, generally predict that protons can decay. The most common predicted decay channel transforms a proton into a positron and a neutral pion, which itself quickly decays into 2 gamma rays. The predicted half-life for this process varies between theories, but typically falls in the range of 10 to the 34th to 10 to the 45th years. Experimental searches have established a lower limit of roughly 10 to the 34th years for certain decay modes, meaning protons are stable on timescales at least 1 trillion times longer than the current age of the universe. But on the timescales now under consideration, even this extraordinary stability becomes insufficient. If protons decay with a half-life of 10 to the 37th years, a value consistent with some grand unified theories, then by 10 to the 40th years, virtually all baryonic matter will have dissolved. White dwarfs, neutron stars, planets, asteroids, dust grains, every object composed of protons and neutrons will have evaporated into a diffuse bath of positrons, electrons, neutrinos, and photons. The positrons will eventually encounter electrons and annihilate, producing additional gamma rays. The universe will contain no atoms, no nuclei, no composite particles of any kind. Only fundamental particles and black holes will remain. The black holes, however, are not eternal either. In 1974, Stephen Hawking demonstrated that black holes emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation carries energy away from the black hole, causing it to lose mass over time. The temperature of a black hole is inversely proportional to its mass. A black hole with the mass of the Sun would have a temperature of roughly 60 nanokelvin, far colder than the current cosmic microwave background. But as the universe cools and black holes shrink, their temperatures rise. A black hole radiates power proportional to the inverse square of its mass, meaning smaller black holes evaporate faster. The evaporation timescale for a black hole scales as the cube of its mass. A stellar mass black hole of 10 solar masses would take roughly 10 to the 68th years to evaporate. A supermassive black hole of 10 billion solar masses would require approximately 10 to the 100th years, a Google years. And so the universe enters its final act. By 10 to the 100th years, even the largest black holes will have radiated away their last energy. The final moments of a black hole's life are violent by the standards of this quiet epoch. As the black hole shrinks to the Planck mass, roughly 22 micrograms, its temperature soars to 10 to the 32nd Kelvin, and it releases its remaining energy in a burst of high-energy particles. Then it is gone, leaving behind only the radiation it emitted during its long evaporation. What remains is a universe in its state of maximum entropy, the heat death predicted by thermodynamics. The cosmos will contain only photons, neutrinos, electrons, and positrons, all at extraordinarily low densities and temperatures asymptotically approaching absolute zero. The average distance between particles will exceed the current size of the observable universe. No gradients will exist to drive any process. No concentrations of energy will permit any work to be done. The universe will have reached thermodynamic equilibrium on the largest possible scale. Time, in a sense, will lose its meaning. With no processes occurring, no events unfolding, no changes taking place, the distinction between past and future will dissolve. The arrow of time, which emerged from the low entropy conditions of the Big Bang, will have run its course. The universe will persist in this state indefinitely, not dead exactly, but quiescent, a vast and silent expanse of nearly empty space-time, cooling forever toward a limit it will never quite reach.